When we create box and pointer diagrams or any other sort of structure and scheme, we're using a space of memory called the heap. Okay, you guys have already heard about the stack. And in the stack, we push things onto the stack. And we pop things off. The last thing on the stack is the first thing off the stack. Now the stack doesn't need to be garbage collected. There is no garbage left on the stack. If everything executes properly, we'll have pushed things on and we'll popped off the same number of things that we pushed on. What are some things that we push on the stack? When do we put things on the stack? When we do recursive calls. So if we were doing a recursive factorial problem, we would push the recursion, the saved elements, the saved state for wanting to multiply by n, and then we would call factorial of n minus 1. And we would keep saving on the stack until we hit our base case, and we would pop everything off the stack and rebuild. So when we drew on the board and we had something that went out like this, well, Scheme doesn't have a board. Scheme has a stack where it's storing those operations. But the box and pointer diagrams structure is stored in a heap. Just a section of memory. We'll call it a heap. Stuff is thrown in there. And because a heap doesn't have this nice sort of structure like the stack does where stuff goes on and stuff pops off, eventually this will be filled with unreachable structures. So we've created a list. Let's see, we define A to be the list of 1, 2, 3. And then if we do a set could or bang on A to be whatever, 4. Well, we start off with A looking like this. That's A. And then when we set could or bang, what we do is we change this pointer here to point to 4. But the 2 and the 3 are still there in the heap. We just can't access them anymore. So the box and pointer structure is still there, and there's areas of the memory that's still marked as being used because we've got that box and pointer structure there, but there's nothing we can do with it. So it's going to happen, and certainly this happened a lot more in the older days when computers didn't have much memory than it does now, but the memory starts to get filled up. So we need some way to get rid of all these things we can't reach. This stuff is known as garbage. And we will do what's called garbage collection. We'll get rid of the garbage. So that's what we're going to talk about today, is how to get rid of that garbage. What I'd like to talk about very briefly is a data structure in Scheme. Yeah?
Can't you just overwrite the stuff if you don't know where it is? Why do you have to write that?
Well, you have to figure out somehow if you can't get to the structure or not. You need to know. It could be, we may actually have, at some point we could have said before this, we could have said define B to be the cooter of A. So at that point we would have set up B to point there. So when we do the set cooter bang, you could say, well, I know I'm getting rid of this cooter pointer, but that doesn't guarantee that there isn't something else pointing to that structure. So we need to have some way basically to figure out what is garbage and what is not garbage. Certainly we don't need to go in and actually erase anything in memory, but we do need to be able to come up with some way to say, these are the free cells I have. And that's what we'll be doing. So in some sense, rather than collecting the garbage to throw it away, we'll be collecting the good stuff. We'll somehow be figuring out what the good stuff is and leaving the rest of it to be used again.
And that's merely because we can't reach the bad stuff.
Because we can't reach the bad stuff. If we can't reach something in memory, then it's useless. So we can write over that. But we need some way to figure out what we can't get to. Because we can have circular list structures, because we could have things where one variable is referring to part of another list. And just when we do a set could or bang, or set car bang, or some mutation like that, we can't guarantee that there's not something else already pointing to it. So we need to be able to do that sort of thing. So a vector is a scheme data structure, which we haven't talked about today before. It's sort of like a list. It's got a bunch of elements in it, and there's an index for each element. What differentiates it from a list is that the time to access is independent of that index. What does that mean? If we have a list and we want the nth element, how long does it take us to get to that nth element? How many steps do we need to take? N steps. We need to cut it down the list n times. But with a vector, we can just go in and pull out the thing that we want. We don't need to cutter down anything. We just pull out what we want. So it's a faster way to access a data structure. And this is a much better way for us to represent our memory, because we don't want our memory access, if we've got a huge memory and we want to get down to the 8,000th cell, to have to cutter down a list of 8,000 elements.
So this is a scheme-specific type data structure? Doesn't exist in
Other languages have vectors, certainly, but Scheme also has it. And there are two commands for vectors in Scheme. Well, there would be more, but there are a couple that we would need to have for garbage collection. Vector ref. And vector ref takes in a vector. Let me just double check that. Yeah, a vector and an index n, and it's going to return the nth element of the vector.
And are elements pairs or are elements single?
So what we're going to have for memory is going to be two vectors. One for the cars and one for the cutters. Okay, so we're going to have two vectors. So our memory, we're basically going to have pairs, but we don't want to have vectors within vectors. It's going to make the accessing harder. So we're just going to have one vector that represents the cars of our cells, one vector that represents the cutters of our cells, and in these two vectors, if we ask for the second element, the second of the cars is going to be the car of the con cell that is the cutter of which is in two of the cutters. That seems to be much more complicated than it had to be. They effectively are going to have two vectors, which we'll represent it this way. This is going to be the cars. That'll be the cutters. So we have two. And then we'll have 0, 1, 2, 3, 4, 5, 6, 7. We start counting at 0 with vectors. For the most part, in computers, everything pretty much starts counting at zeros. In Scheme, in C, the reason things start counting at 0 is that this counter is an offset. So if you're in memory and you've got a memory address, the first element is the address. We don't need to add anything to it. But if we want to get the second element, we need to add 1 to get over to the next slot, or 2 or 3. And that's why we start counting at 0, because we're not adding anything to the address for that first slot.
Did you stop at 7 because 8 elements is like a 5?
No, it just stopped at 7 because I don't want to represent 5,000 things on the board. So this would go on.
Okay.
So we could do it this way. Okay. Up to as much memory as we have for running Scheme. All right, so this will be, so basically in the memory for Scheme, we're going to have a stack and we're going to have a heap. So the stack will be some space and the heap is going to be some other space. So when we need to garbage collect is when our heap is getting filled up. There's one other command for vectors that we should talk about, which is vector set bang, which is reversed. Everything else has been set car bang, set cutter bang, set bang, but this is vector set bang, which takes in a vector, an n, and a value, and it's going to set the nth element to the value. Okay. And effectively, you can think of these as constant time because they're not going to depend upon n. Right? For a vector, we don't depend upon n. We don't need to cutter down a list. You can just think about it as scheme somehow knows if I say 5, just to go whack 5.
Quick question. In math, vectors, they have magnitude and the direction. Is that all analogous to here where they have a box and a pointer, like magnitude and direction? Can you look at it like that?
Well, certainly so the vector has some slots in it, and each slot is going to have some data in it. Maybe. I don't know that I would go so close to actually bring it directly to math that way.
It's like a row of matrix.
Yeah, maybe a row of a matrix. Yeah, I guess we could call it that. But so we've got these cells, and inside them are some data. So let's look at some data. Let's look at a memory where this is the state. Let me draw up these numbers, and we'll talk about what these symbols. We'll talk about what they mean in a minute. Okay. An n before a number means number. A p before a number means a pointer to whatever's that. So this is the pointer to 0, which means we're pointing here. This is a pointer to 4, meaning we're pointing there. And E0 is nil. Okay, so if here's our memory, there's one other thing I need to tell you if this is our memory state. I need to tell you where the root is, how we get into this memory. Question?
Pointing to both the cars and the cutters when we point to something? Like P4?
Right, yeah, so we can draw out what the structure is. I need to tell you what the root is, where we start looking. And the root of this structure is P5. So we can draw what we have for state here. We start looking at P5. P5 is a const cell where the first element is going to point to P2, which is another const cell. So let's just write here. This one is P5. This is P2. P2 is going to point to P0. And P0 has in its first element the number 3, and its second element a nil. We need to do the cutter of P2, which points to P4. P4 points to the car, points to the number 5, and the cutter points to P0. Points to P0. This is the P0 structure. So this cutter here points there.
Could you step through that again? I didn't really follow. How did you start with P5?
So I told you that's the root.
So you didn't actually see that in the vectors?
No, the vectors. So basically, you need to have an additional piece of information. You need to know what the root is, how we start getting into this structure.
We're not starting with that P5 in the lower half of 3.
P5 in the lower. No.
Okay.
No, we're starting with this. This is our root. So I drew a const cell for P5. The first points to P2. If you look at P2, the first points to P0, which has the number 3 and nil in it. The second of P2 points to P4, so I drew another const box. P4 has the number 5 and a pointer to 0. Here's the number 5. But the pointer to 0, we had already created a representation for that structure. So we have to point back to that. Right? It's just like we had defined lists like this, define B to be the cutter of A. We would not actually create new box and pointer structure. We would merely point to the stuff that existed already. And this allows us to do things like EQ. Right? So we don't have a pointer yet in the cutter of P5. P5 wants to point to P6, which we haven't yet drawn. All right, that's P6. And P6 has the number 2 at the beginning. And its car, the cutter rather, is P5. This is what's known as an ugly list structure, but a good example of one in memory. So I just drew this structure up on the board, and what we can do as smart human beings is I can ask you what cells aren't pointed to. And we can look at this and say, well, 1 and 3 and 7. Right. But we need some way to mechanize that for the computer. We can't say to the computer, now go off and draw a big box and pointer diagram. But what we can say to the computer is, start copying things from the root. And when you hit a point where there's nothing left to copy anymore, stop. So that's what's known as, of these two, which one do you think? Stop and copy, not mark and sweep, since we're going to stop and copy. Hence the name. So what we do with stop and copy, the first thing that needs to be done is our memory needs to be divided in half. So for stop and copy, the memory, the heap, is divided in two. These two blocks that we have, which I'm going to represent again only as 8 long, but obviously would be much longer. We have, here's our two memory sections. Where this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We're going to have one area of memory that we're working in. Okay, so that's our working area. And this is going to be a mixture of good cells, which means that they're being currently used, and garbage, stuff that we can't reach anymore. So in our example over here, our garbage is P1, P3, and P7. We can't reach those cells anymore, so they're no good to us anymore. So we have a working area, and we also have an area of free memory. So what happens is we do everything in the working area. And I'm going to copy over the same structure that we have over there. So there's the memory over there. Now in the working area, we're basically going to work until we run out of space to do anything else. Now, obviously, a system hopefully is going to be a little smarter than this. And if the system is idle for a while, hopefully it would take advantage of that time to do some garbage collection for us, not to wait until it was completely filled up. Some of you may have observed this with Netscape. Occasionally you'll wait till your hard drive fills up completely to do its cache cleanup. It's not the most intelligent thing to do, but on the other hand, what Netscape is trying to do is maximize your need to go out to get more information. So we have this working area. We're going to wait till we get full or almost full, and at that point we're going to decide to do some garbage collection. What we do is at that point we stop working. That's the stop part of the garbage collection. And then we're going to copy over the good stuff into our free area. So I need to also tell you over here that our root is P5.
Is that root like a variable binding or something like that where it's coming from? Or?
Basically, there would be a register holding the value of the root into the memory. Right, there needs to be a variable or a register, something holding how we access the memory, where the start of it is. Now, obviously, every time we create a box and pointer diagram, it's not chaining to every other box and pointer diagram that's there. These box and pointer diagrams you can think of are the memories that we're creating, the environments that we create with MC eval. Scheme is doing the same sort of thing. it's creating its environments using box and pointer structure. So the stuff that will be garbage collecting in some will be those frames and the list structures. There'll be two things that will be basically collecting in our garbage collection. It's the frames that we created with the environment diagrams. Remember, we've created frames and they have nothing in them and nobody points to them, and people said, how do we get rid of these? That'll be one thing that we'll get rid of in garbage collection, and also any leftover list structure that we've created.
And do all those things, all the environment frames interconnect, so there only needs to be one route? You can start at one point and figure everything out? Or do you need to know all the pointers to all the environment, all the frames?
Well, so basically what ends up happening when we've got environment frames, so let's say we have some global environment, and let's say we've got some procedure here that has some blob pointing to it. We've applied it, got us another procedure object here, which has got a blob here pointing to it. Then we applied this, got a frame, we applied some other things, got some frames. Okay. What we're going to do, basically our root is going to be our global environment. We're going to start off in the global environment and say, what can we reach? So I start up here in the global environment, which is just a list in our structure, or it could be a vector to make it more easily accessible, faster. And I start off in global environment, and let's say this is marked 1. This is where I start looking. I find this procedure and say, okay, that's good stuff. I'm going to keep that. Now I'm going to start looking here so I can check that off. Now I start looking here, and I say, okay, this is good stuff. It points to this. This is good stuff. That points to this. At this point in time, there's nothing that points here. There's nothing that points here from the global environment. It's gone. That's garbage. These are bad. So we need to get rid of that. So our root is going to point us to the global environment, and then we spin off from there, trying to find anything that we can reach, and if it's unreachable, it means it's garbage. If we can't reach it, we can't use it. No reason to keep it around in memory. Unless we have infinite amounts of memory, which to this day, most computers do not have. The government may have one, but we don't. Okay, so we need to know where the root pointer is. And then the free area, there's going to be a pointer to the free area. So the first free element in the free area. So draw this like that. That's my free pointer. This is my root pointer. The way the stop and copy works is the first thing that we do is we copy over the root. So we're going to take the car and the cutter of P5, which is the root, and copy it to our free cell P8. P2, P6. Now I have copied the cell over. And if something refers back to P5, like P6 does, I don't want to copy it over again. I've already got one copy of it, and that's all I need to make. So what we effectively are going to do is, in this memory, is we're going to leave a forwarding address. We're going to tell anybody else looking back at this piece of memory where we've gone. And they call this a broken heart. So we're very sad. It's moved away. So the car becomes the broken heart, and the cutter becomes the new address. So we're leaving a forwarding for anybody else who's coming to look for us. So now our root pointer, since we've copied root over, moves down here. And that changed to P8. Nothing more will happen to the root pointer. We don't need to change the root pointer again. We've copied the root over. We've changed the root pointer. We're done with that. When we copied the cell over, P8 is no longer free. So we increment our free pointer to the next memory location, in this case P9. Now what we do is we look at the car of the cell that we just copied over. So we need to keep track of how we're moving through these. So we look at P2, we come up here, P2 is still there, it has not been moved yet. So we copy P0 and P4 over. Now that we've moved P2, we change that to read P9, that's where we just wrote it to, and we leave a forwarding address to P9 with a broken heart. So now I've done the car of what I had copied over. Now I'm going to do the cdr. It says P6. P6 has not yet been copied over. I copy its contents. N2, P5. P6 is now in P10. We've copied that data over. And we need to leave our forwarding address. So now I've updated this car, this cdr. We move on to that car. Oh, gosh, I haven't been updating free. Sorry, free's here now.
Between the forwarding address and the broken heart.
Yep. Basically, if you physically move, you need to give the post office a forwarding address. If we're copying pieces of memory over, we're effectively copying the good memory into our free area. Because lists, the structure can be circular, because one part of the list may point back to another part that we've already copied, we need to leave a forwarding address, because what we don't want to happen is if we've got a circular list and we don't leave forwarding addresses, what will end up happening is we'll just keep copying the circle over and over again into the free area, which is not what we want to do. We want to just copy it once. Once we've copied it, then we leave the forwarding address. So we mark the car, they call it a broken heart, but basically you put some sort of mark in the car that says this cell has been moved. In this case, it's a broken heart. And then the cdr is where we've moved to. So we're just saying where in the free area, in this what's basically going to end up being our new working area, where have we moved this cell to?
And we just chose to represent the first one with a broken, I mean.
Yeah, when garbage collection started up, the person who created this particular method, called it a broken heart, and it's been called a broken heart.
Well, what I mean is there's no significance to it being in the car versus the coder.
No, we could write code that would look in the cdr to see if it had been moved and then moves the car. The reason it's a little more efficient to do it in the car is because the way we're copying things is we're copying the car then the cdr. But we could have just as easily copied the cdr than the car. But we're just cycling through like this. So because we're going to look at the car first, it makes more sense to just look at the car. If it's not a broken heart, copy it. You don't have to say, I'm going to copy the car if the cdr isn't changed. A little less efficient to do it that way. So that's why the car changes over to say I've moved, and the cdr changes to be the forwarding address. Other questions?
Are you choosing these in any particular order or reason as far as copying them?
We start with the root, so we copy the root over, and then I just move car, cdr, car, cdr, car, cdr, car, cdr, car, cdr, chaining down that way. So I'm just moving across, copying everything over. So we've done P9, P2 moved to P9, P6 has moved to P10. We've done those two, so now we're moving on to the car of P9. P0 has now moved to P11. We make that change here. We leave our forwarding address up here. That's copied over the car. We've done everything we need to do. We now move to the cdr. P4. We look up at P4. Hasn't been moved yet. We put it in the next free cell. Update our free pointer. So we just copied P4 here and here. Its new address is P12. And then we leave a forwarding address in 4 that we've gone to P12. Are these forwarding addresses going to be used once we've done all the copying? No. It's only for the copying stage that we have forwarding addresses. Once we finish copying, this whole piece of memory is going to be considered free. So we need to finish copying. The car, next car I look at is N2. Nothing needs to be done. It's a number. P5. I go up here and look at P5 and say, oh, it's already been moved. And it's been moved to P8. So I don't need to do any copying there because I went up there and saw that it had been moved already, saw the broken heart, and moved the data. Rather just change the address. Up to car of 11, number 3, nothing needs to be done. cdr of 11, E0, nil, nothing needs to be done. Car of 12, N5, number, nothing needs to be done. cdr of 12 is P0. So we go look up here and say, oh, P0 has been moved, and it's been moved to P11. Now I move into trying to look at the car of the free. which tells me I'm done. There's nothing else that I need to move to here.
What was that last step? You moved in?
So basically, when I stop scanning in cells that have anything, basically when I come here and I say, oh, that's the next free one, I'm trying to look at free, I know that I'm done.
Okay.
Right. So I'm scanning over these. When I scan into the free area, I know that I'm done. So this part here is the copied memory. And this part here is the free area to work with, or the empty area. Someplace that we have a free pointer, we can keep moving. And we can put new stuff in here until we run out, and then we'll need to do a copy again back. When this becomes the copied memory and our empty area, this is no longer the free area. This is our working area. And this becomes our free area.
How does it make that transition? Is it just magic that happens between free area to working area?
Basically, all we need to know is the root to enter in and the free pointer. So it's not really magic. We change the root over when we copy the root over, and our free pointer's here.
Well, at this point, the old working area is not erased yet.
It never will be erased. We don't need to erase it. We're just going to overwrite it. So I had nice, clean, empty cells here when we were copying in. Most likely there was some data from the last time that we had moved this area up here. So it's just things get overwritten. There's garbage that things get overwritten. We don't have this ability in Scheme, but for any of you guys who have programmed in C, you've seen if you do poor indexing, if you do bad pointers, or you forget to initialize some values, you'll get this garbage coming in. That's because there's something in memory already that we're reading in. If you haven't programmed C, don't worry about that. Yes?
As we move down the list, copying things over from the working area into the free area.
Yep.
Did you do that left to right according to the working area, or did you follow the cutters of your
Basically, I copied the root, and I'm effectively scanning. You can think of us having a scan pointer.
Okay.
Where we scan, we say we're scanning this cell right now. So we look at the car of it, then the cutter, and then we scan the next cell.
What's the next cell, though? The next.
Is the next in memory, increment by 1. So
The next up above in the free area, or maybe?
we copy the root,
Yeah.
right? And we copy the root into P8. We look at its car and cutter. We look at the next address in memory. The next address in memory is the 9th one. We were at 8, we go to 9.
So that's just empty, though.
Well, but it's probably been written over. It could be empty. If it's empty, we're done. We copied over the root. If we didn't have anything, if the root was merely 2 numbers in a con cell, it's over. As soon as we scan in and we're looking at an area that's already marked as free, that the free pointer is pointing there, we try to scan there. We go, oh, we're scanned to where the free pointer is. We're done doing our copying. So,
The root's in 8, and the car is P2. You'll copy P2 to 9. And then P6 to 10. Is that what you're asking?
Yeah. I got it.
so we just basically, the free pointer is telling us where to copy to the next cell.
Okay.
And when we scan to where the free pointer is, we know that we've done all the copying that we need to do.
How do you know when to stop if these cells are never empty? You know, like,
We know when to stop because we've got this pointer free. And we're scanning this one. Once we've taken care of the car and the cutter, we scan to the next one. Take care of the car, the cutter, scan to the next one, car, cutter, scan to the next one, scan to the next one, scan to the next one. At this point, when we're scanning, and the cell that we're looking at to scan is equal to what's in the free location. When we're trying to scan what's marked as being free, that's when we know we're done. Right? Do you believe that everything that's good and reachable will be copied this way? No. You believe. Hallelujah. No, you don't believe. Okay, we copy the root over. If there are pointers in the root, we copy those pointers over. Similarly, if there were pointers in the things that were pointed to, basically we just keep chaining down these pointers here, like we did over here, except here I was drawing box and pointer structure. And if there are any pointers that haven't been copied over yet, so let's say something in here pointed to P7, well, I would have had to copy P7 over somewhere in here and then needed to go up here and copy it down and change its address. But because I never hit 1, 3, and 7, it means that anything that was reachable by the root did not point to 1, 3, or 7. Right? Still dubious, or you believe? Believe. It is good to believe.
I have a question.
Sure.
How exactly does this relate to the vector itself? I mean, that's not really clear to me.
How does this relate to the vector itself? The memory is vector. And basically what we do is when we have the scan pointer, we look at the scan pointer, we vector ref the cars on the scan pointer, then we vector ref the cooters on the scan pointer, changing its value using vector set bang based on anything we copy over from here. So that's how we're accessing. I'm saying we're scanning the car, the cooter, the car, the cooter, the car, the cooter, but they're not lists. We're using vector access methods, either vector ref or vector set bang, to change them or to look for them.
Because if it was a list, we'd have to cooter down.
Right, if it was a list, we'd be cootering down it, and it would be fine. It would work. We could represent it, but it would be painfully slow. Right? Memory would be incredibly, incredibly slow if we did it as a list, especially where, since our memory is probably going to be bigger than 16 cells, you just don't want to have to cooter all the way down. So it's much faster to do this as vectors.
Does this then require that only half your heap ever be full?
Yes, right. So this basically prevents us from using all of the heap at one time. So we can only use half of the heap at a time. But it does compact our memory for us. With vector references, does that really matter? Not really. But it does compact the memory. It's not really buying us anything. But we're going to see that this has an advantage over mark and sweep. In this method, we only touch the good cells. We never look at the garbage. This next method that we're going to look at, we're going to have to look at everything. Yes?
What if you have another list structure that's not connected to that one? Do you have another root?
No, you can only have one root, and you can give the root as the global environment.
Oh, okay.
Right? So this, basically the list structure that we built up in MC eval, you can think of that as our global environment, and except that now we'll be using it as vectors instead. And we'll access it there. And if we can't get to a list structure, either box and pointers or some environment frames, through that global environment, it means that it's unreachable to us. Yes?
Why didn't we start using vectors at the beginning of the class rather than just putting them down lists? Write all the programs with vectors.
Because you have to know what element you want.
Right. Well, one thing is you need to know what element you want. You need to be able to cooter down to find what you're looking for. This would be John's expertise. This would be more of John's telling you exactly why, since he knows, he's more familiar with actually why the language was designed exactly the way it was designed. Except that he's not here. He's gone. He's doing problem set 10.
We're only seeing either pointers or numbers. Can numbers also stand for symbols?
We could have symbols in there too. We don't have them represented here. And in fact, what happens with the symbols is that we have one symbol table, which I believe, have you guys heard about this? I think we've talked about the symbol table. No? Very briefly. What happens is if we create a symbol, if we quote something, if we quote A, we use quote A, the symbol table will get A as a symbol inside of it. If we then later use quote A again, Scheme will look up and say, oh, I've already represented that symbol and just pointed to that location in the symbol table. So Scheme is only keeping, it keeps one copy only of a symbol. then points to the symbol table. And since we only get one copy of a symbol in the symbol table, what does this allow us to do to test for? EQ. Which is effectively comparing pointers. Right? If we didn't have a symbol table, every time we did quote A, quote A, quote A, we created new structure, they would not be EQ. If we create a new structure every time, they're not EQ, they're not the same thing. The symbol table also saves us some memory to represent our strings in, because we only need to have one reference to it and then we point to it, as opposed to every time it appears in our code, having to keep remembering it at each location. This allows these cells to either represent a number or a nil or a pointer, all of which are some small bit of bits necessary to represent that information. But if we had a very long symbol, something like the global environment, with all of those characters, we'd need many more bits to store that symbol. And if we needed more bits and we wanted to take a memory like this, it'd be a little bit strange because we'd have to allocate our memory spaces to be for the biggest symbol we could allow. Right? So let's say that we can represent a pointer in 1 byte. Actually depends upon our memory size. A byte is 8 bits. Binary arithmetic, have you guys gotten some of this somewhere? 0, 1.
I'm sorry.
Okay. In the computer, everything's stored as a 0 or a 1. Everything eventually boils down to zeros and ones, and you guys will get to experience it in all its fun and excitement in December. Oh, no. In December, you guys will get to do this. Okay, so basically, you can think of a computer as just being a bunch of switches. Not light switches, but they're switches. There's little gates in there sending ones and zeros, ons or offs, impulses of electricity or not. And everything has to boil down to ones and zeros. So if we take 8 of those ones and zeros together, it's called a byte. 1 or 0 is called a bit. When we get 1,000 bytes, it's called a kilobyte. When we get 1,000,000, it's called a megabyte. These terms may hopefully sound familiar to some of you. Maybe. Hopefully. In any case. So let's say that to represent a pointer, well, if we had 1 byte, if we had 8 bits, and it represents 2 to the 8th locations, right? That's probably actually not going to be big enough for us. How many memory locations, how many things do we point to with only 2 to the 8? 56. So it's not going to be that much. So we probably need to have 3, 4, 5, 6 bytes, depending on how big our memory was. However, each character here needs to be represented by 1 byte. There's something called Ascii code for characters. It's a way to take a character or a symbol on your keyboard over to a number. So every character, a capital A, a lowercase a, a control key, a period, a comma, the return, all of those have an Ascii value. I actually don't think the scheme book has its table in the back, but pretty much every computer science textbook, barring the scheme one, is going to have an Ascii value table in it. Anything that deals with C, Pascal, any of those basic would have an Ascii table in them. In any case, if it takes a byte, if it takes 8 bits to represent each letter, if we had a symbol that was as long as this one, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 21. We'd need 21 bytes to represent the global environment. And if we created a symbol that was even longer, we might need 30 bytes or 40 bytes. And it would be incredibly wasteful for our memory management if we left each slot available to hold something that was 40 bytes long or even 20 bytes long. So the symbol table is going to make us much more efficient, because then we can just have a pointer into the symbol table and we don't need to actually store the symbol in our memory. We'll have a special place of memory that's just holding those symbols, which is a whole lot more than I intended to talk about today. But, hey, you get to know how your computer works now. Yes?
I just just real quick, I can't read this. The second cell in our new working area, what used to be the free memory.
P11, P12.
And did it start as that? Or did
It started at P0, P4.
Okay.
And P0, what was in P0 was copied to P11. So that's why it was crossed out and P11 was written. And then what was P4 was copied into P12, which is why P4 was changed to P12.
And how did P0, P4 get chosen to go in there the first time through?
Because we were just scanning. We copy the root, we scan the car of the root, the cooter of the root. If we hit something that's a pointer, we copy it to the next free cell.
Okay.
So basically, every time we hit a pointer, if it hasn't already been moved, we just copy it to the next free cell. It's very mechanistic.
What was the cooter of the root? P0?
No, P9 it wasn't the root.
P2 points to
P2 points to P0.
Oh, there's a pointer in the car. I got it.
So we had copied P2 into P9. Then we were looking at P9 when we were looking at P0 and P4. Yes?
Is the P's and the N's standard notation like for pointer, number, and nil?
It's a convenient way to notate that, yes. Right. And the book is going to use that, and anybody who's talking about garbage collection and scheme is going to write it that way. But you need to be able to denote in memory whether we're representing. You need to tag the data somehow, because if it's just a number in memory, you need to know: is this an address? Is this a pointer? Is this a number? Or is this nil? We need to know some way to differentiate in memory what we've got. So you could think of it having a little tag field on each memory slot telling us what's in there, whether we've got a pointer or a number or nil. Yes?
How does this thing work for numbers? And some numbers are EQ, other numbers are not.
We still don't know how numbers are done in Scheme. See, there is no symbol table for numbers. And some small numbers are EQ and some larger numbers are not. And I've got to admit that I do not know the dead internals of how they represent numbers.
Mike can explain it to you if you want. The TA. He explained it to us one time, but it's long.
Long and hairy, yes.
I know you've gone over this and I'm still trying to see it is with the free. Is that, I mean, originally things were copied into it and it somehow knew to differentiate that was free copy versus stuff from before.
It's an automaton. It's very mechanistic. If the free pointer is P20, all I say is I can overwrite P20. I don't care what's in there. I can overwrite it. Right? That's all it's saying, is there may be stuff in there, but I've marked this as free. This is my next free pointer. This is the next thing I'm writing into, and I don't care what's in there. I'm just going to overwrite it. So the free pointer, when we go to copy, we take the free pointer and we move it into the half of memory that we are now going to copy into. So the next time we go to copy, the free pointer will come up here to P0. And we just we copy over the root. Once we've copied over the root, this is no longer free. We just copy good stuff into it, so we move the free pointer there. And then we start copying cars and cooters over. Anytime we copy something, we increment free.
Well, why doesn't it look at what's old in 13?
When we're doing free does nothing about looking into the cells. Free doesn't care what's there. Free says put something here. Free has nothing. We never access the free pointer as what's in free. As soon as we copy something, we increment free. Free is always pointing to a place where we can write to, except when we try to walk over the edge of our half of memory, and then we know we need to garbage collect. Right, so we never try to access the stuff in the free pointer. All we do is we write there.
So then the reason it stops is because when whatever was in the car 13, it just needs some meaningless value, and then it's
No, it stops because we have this scan pointer. We're keeping track of where we're scanning. And before we do any copying, what we do when we're scanning is says, are we at the free pointer yet? And when we get here, we say we are at the free pointer, and that's why we're not looking to see what's there. Right? So we're never checking the car or free, because once we scan here, we say we're at free, we've stopped. That's it. There's nothing more to copy. Other questions? Yes?
Do we only have one root all the time, and we have more than one?
There's one root.
Only.
Right. And you can think of that as being the global environment. There's a route to start into the global environment. Right? There's some place at which we start looking.
So with stop and copy, is it possible to utilize more than half of your memory at any one time, or you have to always stay?
You have to break it in half. Are there any more questions on stop and copy, or we could go to mark and sweep where we don't need to break it in half?
You can't do this as you execute.
You have to stop. That's the stop part of it. You can't be executing during this because you don't want to change the state of either piece of memory. If you're in the middle of a copy, let's say I've copied halfway through, I don't want to execute anything at this point because I could do a set car bang or set cooter bang that could blow everything away. So when I'm doing this copying, nothing else is going on. So for those of you who were in the lecture in the afternoon a few days ago, we were talking about environment diagrams, and I said how once I was working on this Lisp machine, actually many times this happened to me, but I used to work on a symbolics Lisp machine, and this was back in the early 90s, and the machine was from the 80s. And it would get to a point where it said, I need to garbage collect, and I'm using the slow method, and the computer would shut down for about 3 to 4 hours. It would try to garbage collect using the regular normal method, but there was just sometimes where we go, warning, I'm going to go in the slow method. Do you want me to do this? Do you not want me to do this? And it would like beep at you for like 30 seconds, but of course it would never give you a chance to actually hit Y or N. It would just be flashing at you, and it goes entering slow method, and you just be like, okay, time to take a nap. So yeah, that was using stop and copy.
So does it have to complete the whole operation before it can do anything else?
Yes.
Yeah.
The entire garbage collection copy has to be done before we can do anything else. Because otherwise we could get into some state where we've copied half, we make changes here or here, and our memory's not going to be consistent at that point.
Now is the speed of the stop and copy, is that like an n squared thing? Or is there like any order of magnitude for the speed?
Well, what is the order of this? How many copies do we need to make?
As many copies as we have good.
We need to copy as many good cells as we have. Right? So there's actually 2n if we count this as car and cooter. So it's linear. We can go through this linearly and basically look at the root, move on to the next, move on to the next. We never get anything circular because of the pointers and the broken hearts which forward us. We never get any circularity going on here. We copy everything once. So it's linear in the time of the good cells. And because the vector references, we can say our constant time. Now, if we had a cooter down the list, then it would be n squared because we'd have to copy n things. It would have to be cootering down the list. It would be actually n times n, but n times m, where m was the length. But we could say that's n squared.
Right.
Yes?
So how does the computer know when to do the garbage collection and what method to use?
The method to use is something that's just built into the particular system you're using. So it's not like the system is going to have a choice, or maybe it might. It might say, well, if I've really hit a point where something has gone particularly wrong, I have to stop and do everything over and fix myself up. But usually, your system is going to use one or the other types. And certainly, breaking your memory in half nowadays doesn't matter as much because there's a lot more memory in computers. And that's not quite as big of a drawback as it was 10 years ago or 20 years ago. Yes?
The actual copying of, say you have something in the free cell that you're considering, there's no corruption of data that's involved from...
When we're copying over, if this becomes my free memory, there's all sorts of stuff up here, but it's not good anymore. So there's nothing corrupted when I overwrite it because there's nothing I was using up there anymore.
But just the process itself is fairly straightforward. It's just like, that might as well not even be there. There's never going to be any potential problems.
There shouldn't be any potential problems now. Because we copy it over, then we look at the stuff here. When we hit the end, we copy it back over here.
It's not like cassette tapes where you have some residue that you hear sometimes that your old Duran Duran cassette.
Although actually you can read memory.
Oh, you can certainly read memory slots that isn't really valid memory anymore, and this happens in C all the time. Especially when you're learning to program C. Huh? Once you write over, it's gone. But all this stuff is here, and we don't have a convenient way in Scheme to access this, and I wouldn't particularly call it convenient in C either. It's usually not a good thing when you're accessing memory locations that are not current and not good. This can create some really bad things going on. This leads, yes?
Is stop and copy then used for modern operating systems and applications? Is that
we really need to worry about garbage collection for the most part in Ascii, where we're creating all these box and pointer structures. In mark and sweep, we get to use the whole memory. Well, not quite. The whole memory, sort of. We need to keep basically a bit array. So we need a bit vector, not an array, where we're going to make our marks. Which is going to be a 1 or a 0. The 0 is going to mean that it's good, and the 0 mean that it's bad.
A bit vector is the same as a bit array. A bit vector is the same as a bit array.
Yeah, I'd rather call it a vector right now because Scheme's calling them vectors.
Didn't
I had said array and said I should have said vector.
Okay.
I had used the wrong word first. So if we had our favorite example, which was and 3, P0 and 4, P0 and 3 and 5, P2. So now we have this corresponding. Okay. We're also going to use the stack here. The main idea of mark and sweep is that we're going to start at the root, which is still P5. We're not doing any copying. What we're going to do is we're going to mark all the cells that we can go to. Mark all the reachable cells. And the way we do this is we're going to start at the root, and we're going to check its car, then its cooter. But what's going to end up happening is when we check the root's car, we're going to go to P2, where we're going to check P2's car and cooter. Because we're not copying anything here, we need some place to remember what we need to go back to. In this method here, because we had copied the cells, it was easy for us to scan over them one after the other. Here, once we make a mark, once we mark root being good, there's no way to differentiate that mark from any other mark. All right. So this starts out all with zeros. So the first thing that we do is we mark the root as good. Let's put it in here. So the root is good. I am going to go off and check P2, but I'm going to push P6 on the stack so that I remember to come back to it. So now I go to P2. And at P2, I am going to mark that I've got a good cell. And I'm going to check its car, but I first want to push the cooter onto the stack so that I remember to come back to it. So now I go to P0, which I can reach, and I put a mark. Now, at this point, I want to check the car and the cooter. There's no pointer at the car, so I don't need to push anything onto the stack. This is nil. There's nothing I need to do. I have reached the end of the chain that I can reach this way. So basically, I followed the car of P5, our root, and then followed the car of that cell to the point at which I couldn't hit anything anymore. So now I've hit everything I can. So I go over to the stack and say, oh, now I want to look at P4, which I would pop off the stack and it would go away, but I'm just going to cross it out so we remember that we had it on there. It'll be easy for us to follow. We pop P4 off the stack. We go to P4 here, and we mark it as reachable. It's good. We check its car. It's just a number. Go to its cooter, P0. We come over to the P0. It's already been marked. Done. Go to the stack, take the next top element, which is P6, pop it off the stack, come to P6, mark it. Car is just a number. Cooter is P5. We look at P5, it's been marked. We are now done. We have now marked everything that is good. And everything that is bad, that is garbage, is marked with zeros. Okay? So that's the mark phase. Check. Now we need to do the sweep phase. Right? What are we likely to be doing during the sweep phase? What do we need to know? What do we need to do right now? If I want to write something into this memory, what do I need to know? What's free? Where is free and how do we get there? So we find the first free cell. 1. Oh, there it is. And there goes my free pointer. Okay. And now what we're going to do is we're going to make a chain of the free cells. So what we're going to do to make the chain of the free cells is at the free cell here, I'm going to change its car to nil, and I'm going to change its cooter to the next free cell that I find. So I'm going to scan. I'm going to be scanning here, then I scan here, then I scan here, here. Oh, that's a 0. I found my next free cell, so P3 is going to go there. So here this will change to nil. And then we're going to scan up, find the next free one, which is P7. That goes to E0, and there's no more memory left. So that's E0. We've basically built up a list. We've built this list of pointers up that allows us to point to the next free cell.
So we don't bother collapsing it down, so moving cell 2 down to 1.
Right. There is no, effectively, compression of memory. We're not compacting. This compacted everything down. This one does not. Okay. This one, however, allows us to use all of the memory. So we can use all the memory, which I wrote up there anyway, sort of. All memory minus a bit vector.
How many bits are each cell? We said they were pointers, so they were...
It's going to be as many number of bits as we need to represent all the addresses in memory.
Okay, would that be usually 3 or 4 bit or 5?
Oh, it's certainly going to be more than 3 or 4 bits.
32.
Because if we only had 4 bits, we can only represent 16 numbers.
Oh, right.
So we're probably going to have more than 16 addresses.
Okay.
It might be a 32-bit address. It might be a 64-bit. So we don't know.
We've got here is really only like
So this, right, it's not very much of our memory at all. It's just one single bit for every 2 cells here. So if each of these cells is 32 or 64 bits, we're not taking up that much memory by this.
Isn't there also some memory that's occupied by the stack?
Certainly, right, yeah. The stack is part of memory. The heap is part of memory. There's a symbol table in memory. There's some registers that we have. Registers, as you learned yesterday, are not memory, though.
So this method would use, I don't know, 95% or 90% roughly? Is it?
Well,
the
basically,
stack would be like 5% maybe.
right. This is going to utilize. Well, you can look at it as whatever we have allocated for the heap space is we're going to use all the heap that we have allocated. Whereas this is only going to use half of the heap that we have allocated. So we can compare versus the heap size. So here we can only use half of what we allocated for the heap. Here we can use everything that we've allocated for the heap. However, let's talk advantages and disadvantages here. What if I have amazing amounts of garbage? I've only got 3 good cells in 500. Which one of these 2 methods is going to be faster? Stop and copy. Because in stop and copy, I only touch the good cells. I'm going to copy the good cells, and I never look at the bad ones. Whereas in mark and sweep, I touch all the cells,
So is this
whether they were good or bad.
that you're machine was using? Was it mark and sweep?
I actually don't know which method it was using, but it was painfully slow. It could have been either one of these. But when it came at like 1 or 2 in the morning, it was actually convenient because you could justifiably go to sleep. So,
For 3 hours.
huh?
3 hours.
Yes. Yeah, I slept on a couch and would get up. Yes.
We said that stop and copy was linear. Mark and sweep.
Well, what's mark and sweep going to be?
It's also linear, but
It's linear,
looking
but
at all of the memory.
right, we're looking at all of the memory, and so basically they're both linear, but the ends are different. But linear is linear.
Okay.
Because basically what we're doing with orders of growth, we're looking at n large. Right, so we're not looking at cases with n small. It's n large, and linear is linear is linear. Yes?
Are there any disadvantages to the apparent fragmentation of the memory result from mark and sweep?
Well, I mean, in some sense, what the fragmentation means is that we have to actually go through and chain our free pointers to make up this list. Where we've got this compression here, we've got a nice compact place where we're going to put all of our cells in the free space, and we don't have to actually go through and do any sort of chaining to figure out where we can go through for our next free pointer. It's just, we just increment each time. So that's that one. 2 different methods. Both get rid of garbage. Both make more space for us. More space is good.
Now, these are methods that could apply to any programming language, essentially. That it's not just scheme.
Sure. Yeah. Except that scheme, basically in languages like C and Pascal, when we declare the program, how many of you guys have done C and Pascal? So that
Pascal.
Okay, so about half of you. We declare variables in these languages, and in BASIC too, right? So we have to declare variables, at which point at the compile time, we create slots in memory for these variables. Scheme is a lot more dynamic. As we're running Scheme, we can build up lists, we can take lists apart, and do all sorts of stuff like that. Now, C certainly has some dynamic capabilities. We can malloc memory. If you guys don't know about C, don't worry about this. This is just for people who've heard of C and know about it. We can malloc memory, but then we free it up. So in a sense, in C, we're doing, John walks in and goes, oh my God, they're talking about C, wrong language. But in C, if we go into some extra part of memory, if we malloc to get more memory, we, as the programmer, have to put in a free command, a call to a free function to free that memory up. So in a sense, in C, we're sort of providing some of that memory management. In Scheme, we don't worry about it. It's all there and taken care of for us. We can just keep chaining out the lists. It'll garbage collect when it doesn't have anything left.
But the free command that you would use in C would be equivalent to these guys. It would do the same.
No. So basically, in C, when you basically say, when you malloc to get a chunk of memory, when you free it, you just stop pointing to it.
Okay.
So in a sense, we stop pointing to it, but we never do a full scan of memory on a free. On a free, we just say, there's a particular element that I created before, and now I don't want it anymore. So it's just like letting go of one pointer, which we can do here by set carbang or set cooterbang.
Right. But that wouldn't do any garbage collecting.
No.
That would just
No.
It's just like this mark. It just marks the ones and the zeros at the bottom.
Right, it's basically marking what's good, and when we free it, we mark it with a 0.
Okay.
So the C program is providing some of this garbage collection handling. So we're effectively unmarking or marking it as good.
Do you know how Java does garbage collection?
No, because I've never written Java code.
Is it just that some languages have garbage collection and some languages don't? Is that the deal? Like C and Pascal, it's all about allocating and deallocating?
Yeah, I mean, there are certainly different language types. There's different things that they're doing. And in Scheme, we can create a lot of structures on our own, and then they're sitting there waiting. All this box and pointer stuff sits there and waits because we can point at it from any number of ways. But in a language, a declarative language like C or Pascal, we say, we want a variable in memory, and there will be a slot there. From basically, we compile it. When we start running it, that slot is there. And when we stop running it, then the slot goes away, but the slot's there the whole time. Right? So basically, right, Scheme is much more dynamic. Right? It basically allows us to keep creating new things, whereas you can think of C in some sense as being very static. When we start running, we get some chunk. And we can do some dynamic memory allocation in C, which I assume Java is going to be a lot closer to C than it's going to be closer to Scheme.
You still declare variables in Java, but there is a garbage collector. So
Okay, yeah.
how both exist
Hmm.
at the same time.
Yeah.
As far as operating systems in relationships to programming languages, this may be off topic. Totally shut me down.
It's not a matter of shutting you down. It may just be an answer I may not be able to answer your question. I certainly don't want to discourage questions, but sometimes I may not be the right person to answer those questions for you.
Right. So the operating system itself, it seems like it would make use of both of these, depending on the situation. And
It could. We could certainly write an operating system that might use one or the other. You could.
Operating system that only uses one of these.
Does the operating system do garbage collection in this kind of a style?
It has to allocate. It boils down to allocate.
It's whether you're thinking about the operating system doing it or Scheme doing it. And in some sense, in this case, Scheme is actually doing the garbage collection. Scheme knows when its space for its heap is running out, and Scheme is doing it. It's not the OS doing it. Scheme is doing this management.
The operating system does give something to Scheme.
You okay, Anthony? Yeah. I'm sorry, let's get back to your question.
Okay, so in this case, the operating system is given memory to Scheme to do with what it will.
Right, and Scheme has to manage that memory for itself.
Right. And at some point, Scheme will also say, as an application, that, hey, I'm done with this memory, or I'm not done with it. At some level, it's talking.
Right, so the operating system at that point might just mark it all as 0 and say it's not being used.
It's considered a compiled application at some level, and where it is a compiled application, it has to deal with the operating system. And the reason I was thinking about this is because, I've worked with most of the languages that are compiled, and so there is this sort of deference kind of a thing going on where you do have to be aware of what the operating system is thinking. So, I don't really have any more questions.
Ascii, is there a question there?
There was originally.
Okay, yeah.
I think getting back to the question, there was a footnote.
Can somebody tell me the question?
There was a footnote in the book that talks about mark and sweep versus stop and copy, and saying that stop and copy was generally better when you have to use virtual memory. So that makes me think of operating system, because if you're using stop and copy, when you actually have to write some of this information to virtual memory and access it on the disk, it's much easier to get to it because everything's close together rather than having to page back and forth across a long list. So that gives me the impression that it is used by the operating systems as well.
Well, certainly operating systems need to have memory management. I mean, that's a big part of operating systems. I don't think you guys are getting an OS class here. And I can tell you that I never took one, which is why I don't know the answer to some of these questions. I never took an operating systems class. It's not required as a CS major or as a PhD. That's not where I specialized. There are certainly people who can answer all of these questions for you. And even though John didn't specialize in operating systems, I guess he would be that person. But he came by and left. So other questions that I might be able to answer.
Does the computer have a way of knowing the proportion of the memory that is garbage?
No.
No, because it's not really.
Has no idea, right? In Scheme, we can do so many things with pointers and set carbang, set cooterbang, moving stuff around, whack, 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 whack. The computer has no idea. The only way for the computer to know is to somehow scan through the cells.